The entire food system runs on a single chemical compound. Not fertilizer, not water, not diesel. Ammonia. Every year, we synthesize over 180 million tons of it, using a process that hasn't fundamentally changed in a century. Half of that goes directly into the soil to grow the crops that feed half the planet. But the other half, a staggering 90 million tons, is used for something else entirely. It's the hidden fuel for the most critical industrial reaction on Earth, one that happens inside a metal tube at 500 degrees Celsius. Without it, the global supply chain doesn't just slow down, it stops moving. This is the energy historian, uncovering the hidden systems that power civilization. And the story of how we feed ourselves is not a story of farms, it's a story of catalysis, pressure, and a single reaction that keeps everything from stopping. First, the bottleneck isn't the farm, it's the port. Modern agriculture is a just-in-time system stretched across continents. A combine harvester in Iowa, a packing plant in California, and a supermarket in New York are not connected by road. They are connected by a sequence of synchronized handoffs. The grain is harvested, stored, loaded onto a train, moved to a river barge or a silo, transferred to an ocean-going vessel, shipped across an ocean, unloaded, processed, packaged, and sent to a store. Each of those steps is a transfer point, and every transfer point is a potential failure cascade. The system only works because each link assumes the next link will be ready at the exact right time. A delay at any node doesn't just pause that shipment, it forces a reroute of everything behind it, collapsing the schedule. The entire logistics web is balanced on the assumption of predictable flow. Remove that predictability, and the chain reroutes itself into gridlock. Second, the system depends on a fuel that is also a feedstock. Diesel. It powers the tractors, the trucks, the trains, and the cargo ships. But its importance goes deeper. Diesel is the workhorse fuel because of its energy density. It packs more punch per gallon than gasoline. That's what makes long-haul trucking and ocean shipping physically possible. But here's the catch. The same industrial process that cracks crude oil into diesel also produces the chemical precursors for plastics, solvents, and synthetic rubber. The refineries that make your diesel are also making the components for the pallets, the shrink wrap, the containers, and the hoses that move the food. So when diesel supply tightens, you're not just competing with truckers for fuel, you're competing with the entire material basis of modern logistics. The price of moving food is tied to the price of making the things that hold it. Third, the most fragile component is the one you never see: refrigeration. The cold chain is a continuous, temperature-controlled environment that stretches from the packing house to the supermarket cooler. It's not a luxury, it's a physical necessity. Without it, the variety and safety of our food supply collapses to what can be dried, canned, or eaten locally. This chain runs on electricity. But not just any electricity. It requires highly reliable, always-on power. A refrigeration unit at a distribution center, failing for 4 hours, can spoil millions of dollars worth of product. A brownout at a port can thaw an entire shipload of frozen meat. The cold chain is a massive, invisible battery of stored cold, and it's constantly leaking. We spend enormous energy just to maintain the temperature gradient between the inside of a container and the outside world. The entire modern diet is built on this ability to fight entropy, 1 kilowatt-hour at a time. Odyssey. Now, this is where the single chemical comes back in. To make ammonia, you need hydrogen. You get that hydrogen by stripping it from natural gas. And you need nitrogen, which you get from the air. The Haber-Bosch process smashes them together under immense heat and pressure, using an iron catalyst. That's how we make fertilizer. But we also use that ammonia for the other critical reaction: selective catalytic reduction. Inside the exhaust system of every modern diesel truck, train, and ship engine, a precise mist of ammonia solution called diesel exhaust fluid is injected into the hot exhaust stream. A catalyst there breaks down the smog-forming nitrogen oxides into harmless nitrogen and water vapor. This isn't optional. It's what allows these high-compression diesel engines to meet global air quality regulations. No DEF, no legal over-the-road transport. The system that grows the food and the system that moves the food are now competing for the same chemical output from the same ammonia plants. One facility quietly sets the price for millions of meals. The timeline for food is now set by chemical plant maintenance schedules, not harvest cycles. This creates a terrifyingly narrow funnel. Global ammonia production is concentrated. A handful of countries with vast natural gas reserves, Russia, China, the United States, the Middle East, dominate output. A disruption in the gas supply, a catalyst plant fire, or a geopolitical sanction doesn't just affect fertilizer prices. It threatens the very legality of the trucking fleet within weeks. During the 2022 natural gas price spikes in Europe, ammonia plants shut down. Fertilizer prices soared. But the hidden clock started ticking on the DEF supply. If those plants had stayed offline, the trucks would have eventually hit a regulatory wall. They would have been forced to stop running, not for lack of diesel, but for lack of the chemical that lets them burn it cleanly. The food supply chain is protected by a layer of environmental regulation that depends entirely on the continuous output of a separate, energy-intensive chemical industry. Fourth, the system has eliminated all slack. For decades, the relentless drive for efficiency has squeezed out buffers. Inventories are lean, warehouses are automated and optimized for throughput, not storage. Ships are built to the maximum size that can fit through the Panama Canal. This hyper-efficiency creates phenomenal cost savings and abundance, but it also creates phenomenal fragility. There is no longer a warehouse of America holding months of supply. The inventory is in motion, on trucks and ships and trains. This means the system has no shock absorber. A delay doesn't create a temporary shortage while reserves are tapped. It creates an immediate shortage, because the reserves are the trucks stuck in the delay. The system's resilience has been traded for its efficiency. It can handle tiny fluctuations, but it cannot handle a simultaneous shock to its energy, its chemical, and its logistical layers. Fifth, and finally, the ultimate dependency is on synchronization itself. The modern food system is a just-in-time network built atop a just-in-case planet. Agriculture is seasonal, weather-dependent, and geographically dispersed. Logistics require perfect timing across global distances. The energy and chemical inputs require steady, uninterrupted industrial output. These three timelines, biological, logistical, and industrial, must remain in phase. A drought in Brazil delays the soybean harvest. That delays the ship loading in Santos. That ship missing its berth window in Shanghai delays the return trip of the empty container. That container not being back in California. The system appears stable until one catalyst fails. The entire network only works because every chemical plant, every ship engine, and every harvest schedule is perfectly aligned. So, what holds it all together? Not a central planner, but a series of contracts, futures markets, and real-time pricing algorithms that constantly reroute flows around disruptions. It's a system that uses price as its nervous system. When a bottleneck forms, prices spike at that node, attracting more supply or diverting demand. This works beautifully for marginal, temporary problems, but it has a critical weakness. It cannot solve for a simultaneous failure of multiple, non-substitutable inputs. You can't price signal your way out of a global ammonia shortage because there is no substitute for the catalyst in the exhaust pipe. You can't auction your way out of a synchronized port closure if every alternate port is also full. The market is a brilliant optimizer, but it is a terrible architect of resilience. It will happily strip away all redundancy to chase the last dollar of efficiency until the moment the system snaps. The human anchor here is invisible. It's not a farmer. It's a logistics manager staring at a dashboard at 3 a.m., watching a storm cell move over a key rail junction, a chemical plant outage alert flash on another screen, and a carrier notification that a ship is slowing down to save fuel. Their job is to mentally simulate the cascading delays and reroute shipments through paths that still have capacity. They are the human nodes in the system, making decisions with imperfect information, trying to keep the rhythm from breaking. They know the fragility intimately. They know that the abundance on the grocery store shelf is the output of a dance that never stops, powered by a chemical reaction that must never fail. When pressure hits this system, the cost isn't distributed evenly. The financial pain moves to the weakest links first: the independent truckers, the small farmers, the food processors with thin margins. They absorb the volatility. The largest players, with long-term contracts and vertical integration, maintain control. The asymmetry is built into the structure. The system that feeds nations is stabilized by transferring risk away from its core and onto its periphery. The quiet realization is this: we have built a civilization-scale metabolism that requires constant, synchronized inputs of energy, chemicals, and motion. The food on your table is the output of a planetary-scale chemical engineering process. Its stability is not a given. It is a daily achievement, a precarious balance between biology, industry, and logistics. It works until the day the catalyst doesn't arrive, the temperature rises, or the synchronization fails. And on that day, the distance between the farm and the fork becomes very, very long. If this system came under real strain tomorrow, what fails first? The trucks, the cold storage, or the fertilizer supply? Think about the chain you just saw. If this gave you a new perspective, hit subscribe. The hidden infrastructure is always there. Now you know where to look.